Hey, what's up guys? My name is Cherno. Welcome back to my game engine series. So last time we talked about time steps and delta time and all the kind of timey things that we needed to talk about. Definitely check out that video if you haven't already. And we actually are moving towards kind of a complete little minor kind of system that we have for making 2D renderable kind of objects and interaction and world games, I guess, right? Because what we have at the moment is like we've got a camera system, we've got a little camera system, we've got ways to kind of submit geometry for rendering. We've got the ability to like respond to key presses and all of that kind of stuff and move not move objects yet, but just move the actual camera and do all of that fun stuff. We've got a proper kind of renderer flow, right? So the next step in kind of continuing on with this trend is how do we place objects in different places in our world, right? So at the moment we only have the ability to put all the objects as like the objects will be rendered according to their vertex positions, right? So we have like we're rendering a triangle, we're rendering a square or a rectangle. It's a square. It used to be a rectangle because of the projection matrix, but now it's a square. So we're rendering all of them kind of at the origin, or really like it doesn't have to be at the origin. It's whatever the vertex positions like say, that's where it gets rendered. But what I want to do, and what we need to be able to do, is actually say that I want to render this object with a particular transform, right? And that transform is something called like a model matrix. Essentially, it's like a world matrix which describes like the position, the rotation, and the transfer. Sorry, the position, the rotation, and the scale. So the transform of the actual entity in the 3D world that it's in, right? And that's primarily how objects get put into their respective places in the world, right? We have, like if we look at this bunny, for example, right? We have this kind of bunny. This is our 3D model. So the actual bunny is made up of various vertex positions and other vertex attributes, right? Like normals, texture coordinates, that kind of stuff. But all of these vertex positions are just relative to each other, right? They're not relative to where it is on the world. I could put the bunny here. I could put the bunny here, right? However, that shouldn't have any kind of effect on the actual vertex positions. Why? Because when we model the bunny, we model it like at the origin maybe, or just on top of the origin. So it's like on a ground plane like that. We build up all the vertices. And that's kind of the bunny that we end up with, right? And then when we actually render it inside a 3D world, we apply an additional transformation to those vertices, which tells our computer where in the world we want to actually render this bunny, right? That way, we can use the same bunny model if we want to render something here or there, right? If we actually wanted to only render according to vertex positions, we'd have to modify the vertex buffer of the bunny, or create two different bunny objects or models, or two different bunny vertex buffers, because we want one bunny here and one bunny here. That's not what we want. We want to render the exact same set of vertices. However, we actually want to transform that set of vertices by a certain amount, right? Whether that be translation, which is where it is in the world, rotation, which is how it's kind of rotated or oriented, and then scale, so how kind of big or small it is. Right? All of that is a transformation matrix, and we need one of them for every single object that we really want to render. And in the grand scheme of things, most game engines use something called an ECS, an entity component system, or like some kind of form of composable game objects, where basically we have kind of a set of components and they are composed together into like essentially a game object, right? So if we look at like an entity component system, what that basically says is that everything's a component, right? And then we have a set of data associated with it, and then we have a bunch of systems associated with that as well. That's eventually what Hazel will have, some form of ECS or CGO or something like that, right? But until that's the case, because in that scenario, then the transform will actually be a component that's probably like it is in most engines, mandated to be on all objects. It doesn't have to be, because you can, if you think about it, an entity or a game object could be something that doesn't actually even get rendered. And in that form, it might not need to have it like a transform or anything like that. But for everything that gets rendered, we'll have a transform component, which is where that data is stored. We don't have that at the moment. I'm going to just put this bunny down, I think. But we don't have that at the moment. So what we have instead is just this kind of Hazel renderer submit call. That takes in a shader, that takes in a vertex array. That's where we're going to take in a transform. So we're basically saying, I want this mesh, which has a material, which is our shader at the moment, and our vertex array, which is our geometry at the moment. They'll eventually be collapsed into just one mesh object. we want to submit that and we want to render it at a particular transform. And of course, transforms have to be per mesh, right? They have to be per object. They can't be for the whole scene. Our camera's transform is usually for the whole scene, right? That's what we talked about in the cameras video. But for actual meshes, for 3D objects that we render, we need a separate transform for each kind of object. That's why it's kind of put into that section of the code. Anyway, this is cool because we're going through and we're creating all this kind of low level kind of stuff that eventually this is going to be so abstract that you guys will have no idea how it's going to work. Like, I promise you, like, what's going to happen is that Hazel's API will change so much. I mean, we're doing so much stuff in even C++ now that will never be done in C++ in the future. We'll have a level editor. It will serialize certain files. Those files will be read on startup. That's how our objects will be created. It'll be so like hard to understand how Hazel works that I really am happy with the way that I'm kind of explaining all this and taking time to actually set this up in this kind of way. Even though it is somewhat temporary, and I'm obviously not writing final engine code straight away because that would be basically impossible and really boring to do. What I'm doing is I'm actually showing you guys how everything works, and I think that's really cool because seeing an engine kind of work from this phase before you start like creating an ECS and doing all of that stuff. First of all, it helps you understand why we even need an ECS and actually what the ECS at the end of the day is going to do, because it's really going to do the same thing that we're doing here. It's just going to be in a much more abstract and powerful way, right? Much more flexible way. Whereas this is kind of just tied down a little bit. But anyway, let's jump in. Let's take a look at the transformation matrix and how we can actually render our triangle and our square at different transforms. And one other thing that I want to say is that even though it might appear that we're rendering 2D objects in this case, I mean, obviously all this rendering is kind of 3D, and the theory behind everything I'm explaining, like, meshes, materials, vertex arrays, transforms, all of that stuff, this is really applicable to a 3D renderer. If we built a 2D renderer, we would do it differently, right? Like, we wouldn't have a material system, for example. We don't really have a material system, but we wouldn't be submitting geometry with shaders, right? For example, we just wouldn't be doing that because pretty much all the geometry would actually have a single shader, right? It would be like our 2D material shader, right? And then also we wouldn't be, just like a lot of the way this stuff is written is specifically for 3D, right? Like we wouldn't be submitting a transform either. So no shaders, no transforms, none of that. Because what actually happens is when you request to draw like a 2D primitive, like a square, basically everything in 2D rendering is going to come down to being like a quad. When you actually do draw a quad in a 2D system, you'd actually batch that into like a big vertex buffer with other quads that you want to render so that you can do it all in one draw call with one shader, right? Whereas with 3D kind of rendering, you typically, you can batch things together, obviously, and you can try and sort things into a particular render order so that you kind of group things together. So everything with this material should get rendered at the same time. But in general, you basically render every object with a separate transform and a separate material potentially, right? Whereas in 2D, it's very different. So this might look 2D, but just keep in mind that this theory is all applicable to 3D. And in fact, when we do touch on specifically 2D rendering in Hazel, which we haven't done yet, at that point in time, that's when I'll kind of explain, I guess, more of the differences and also how we would do this in 2D. Before we jump into the code, just want to give a huge thank you to all the patrons. Patreon.com/the Cherno is where you can go to help support the series. You'll get rewarded by like just getting videos early and also getting access to like group discussions in which we talk about the future of Hazel and all that stuff, and also access to the Hazel development branch, which is my kind of private development branch for Hazel, in which I've basically done all of this stuff and more, like PBR rendering, 3D rendering, really cool stuff. There's basically like a full level editor there, right? There's a whole like viewer and everything, and you can even just plug in your own textures using UI, and there's a lot of stuff you can do. So definitely check that out and help support the series. Let's jump in and take a look at model matrices and transforms and all that stuff. Okay, so as I mentioned, we have this kind of begin scene, we have this kind of submit, and then we have an end scene. That's kind of the actual flow of our renderer. So what we actually want to do now is, upon submission, we need to position our object in the world. So what we're going to do is basically plug in some kind of transformation matrix as a third parameter into here. So the way we'll do that is we'll go to submit, and then inside my submission here, I'm going to add a third parameter. This is going to be const glm mat4 transform. Okay, that's it. It's just going to be a transform matrix. If we go over here into submit, we'll add that in. Okay, and then what's going to happen is Very, very simple. Just the same way that we kind of submit this or we upload this view projection matrix, right? We're going to do the exact same thing every time we submit with the model matrix. Now, here's the difference. So over here, I'm uploading the uniform mat 4, which is our view projection matrix, into this shader for every single submission, whereas I don't actually need to be doing that. I only need to really do that once per shader per scene, right? So that's kind of, this does not need to be done every time. It's done every time at the moment because we don't have any kind of global state. And also we're using 2 different shaders now anyway, and they do have to be updated. But if you're kind of using a single shader or a single kind of material across all of these things, you can actually just upload that uniform mat 4 once and then render all the objects as separate draw calls without having to update that. But with this one, we actually, like with this model matrix, like, right? So I call it u_model matrix. This actually does need to be, and I don't know, like I call it model matrix. Transform might make more sense, to be honest. So I'm actually going to call it transform. I wasn't planning to, but I just did. What we're going to do is submit this transform into here, right? So this needs to be done per object. Every time we submit, we absolutely need to do that. Now, in a renderer that doesn't render things immediately like this and actually does queue it up, you'd probably copy this actual transformation matrix into like a 64 bytes. You'd copy those 64 bytes into some kind of buffer that would basically kind of be like part of your render command. Because typically when you render, again, 3D objects, right, you want to actually render them at a transform. That's normal. That's how rendering works. So if we go back to Sandbox app, and what we could do again is just by default, you know, if I go to the header file, by default, I'm just going to set this to glm mat4.1, right? And what that's going to do is just basically give us the identity matrix, which means no transformation matrix, right? It's going to apply no transforms, the same as multiplying with 1, right? So that we don't have to necessarily submit a transform if we don't want to. And that way, like if I was to just launch this code right now as is, without actually adding a transform, it should render and we should get the same result as before. And I mean, obviously I haven't even set up any of the actual uniform, so that's probably going to be useless doing this. So let's go ahead and set that up now, right? So we have, I'll just get rid of this. So we have our view projection, and then we're just going to copy that. And underneath that, we're going to have our u_transform, right? And so what we're going to do is we're going to multiply view projection by transform, and then by our vertex position, right? So we're just adding that in, and we'll do the same. So I'll copy this and add that into our blue shader vertex source, right? So we have this obviously inside our vertex shader. And so now we have the view projection matrix and the transformation matrix being multiplied together with the actual vertex position. Okay, so that should now give us, I mean, we should test this right now with absolutely no transform and make sure that we have the same result as before, which was just kind of like the square and the triangle in the kind of same position, right? So if we do that, yeah, we've got that, and then we can move the camera and we can rotate the camera and everything works in the same way. So what I'll do now is I'll actually plug in a matrix. So because I'm going to want to actually play around with this and not just have a boring old matrix in here, what I want to do is actually make the matrix over here. So we have the camera position, that's all great, but I also want to have a little transform, which I'll call square maybe transform, right? Which, and this thing is actually going to be, actually, you know what? I'm just going to make a vec3 instead, called square position, right? And I think I can just by default set that over here to 0 because we need to initialize it. And then what I'll do is, so left, right, up, down, that moves the camera, right? What I might do is just make the I, J, K, L keys, because like A and D is already taken for rotation. I don't want to mess with that. But what I'm going to do is I'm going to basically copy this if statement and implement it for, so left will be J, right will be L, I will be up, and down will be K. So the I, J, K, L keys, right? I'm going to take those and make them actually move our square position. So now we should be able to move the square, which will be quite cool, I think. So we're going to move it by, so it's got camera move speed, which is like fine, but I think what I'll do is I'll copy that and I'll just make a variable called square move speed, and I'll just set it to like 1. We'll make it quite slow. So we'll say square move speed over here, square move speed, and of course we need to multiply it with delta time as we're doing. And now we have square position. So now we're ready to make the matrix, okay? So what I'll do is I'll say glm mat4 transform equals glm translate, and then we can just literally put in our square position, and that's it. And we need to provide a matrix that we want to transform, square position. Okay, cool, right? And that should just work, right? Now for translate, we'll need, I think we did this inside camera. So let's just grab, yeah, we need this include to make that happen. So we'll just paste that in there. And now this should just work, right? So I can just render my square with that particular transform. So let's go ahead and just run that and see what happens. So now if we use the IJKL keys, we should be able to actually move our square around, which should be cool. And you can see I can do that, right? And you can see it's moving separately from the triangle. Now, if I move the camera, it's going to move both of them, right? And it's going to move them the kind of opposite way. Whereas this will just kind of move it like that. So that's really, really cool. Now, here's what I can do that's pretty cool as well. I can actually render a whole bunch of these. So at the moment, we're just rendering just one square, and it's actually quite big. But what I could do is actually use this to render some kind of tile-based system, right? Now, obviously, the examples I'm giving here are just kind of so that you understand how the transformation works, not how you would render a tile map, because you clearly would not render like a whole tile map using kind of 3D rendering where you just, you know, have everything as a separate object with a separate material and do all that, because that's very slow. But just to give an example, what you could do is have a little for loop that, let's just say I just want to render like a bunch of these, like 5 of these in a row, right? So what I'm going to do is I'm going to submit, and I might just not render the triangle for now. So they're very big right now, which is fine, but they're quite big, right? I don't want them to be so big. So what I'm actually going to do is use my scale, right? I'm going to make a glm mat4 scale. I'm going to make a scale matrix, right? That's just going to basically, and we'll start off with this. It's basically going to just scale down our cube and make it like 0.1, right? So it's going to be 0.1 of the scale that it used to be, which is basically 10% as big, right? I'm making it a lot smaller. So we've got my scale, I've got my position, right? And my position is going to be, we'll say glm vec3 position, and then we'll just, maybe we'll start it off. So how big is this going to be, right? If we look at what this is, let's just try and work this out. So it's 1.5, right? So 1.5 by 1.5 is how big our actual, I kind of want to make it 1. You know what, let's modify this and let's make it 1 unit. So basically the square right now is going to have a width and height of 1 unit. So with that in mind, this is going to make it 0.1 units, right? So what I'll do is I'll set the position, the x position, to be I times 0.1. If I do that, what it's going to do is it's going to space everything out by 0.1. That's not that great. I'm going to add 0.11, right? So that'll leave a little bit of a gap between each square. I'll set this to 0 and that to 0. And then what I'll do is I'll construct my matrix. So this transform, I'll take down, I'll put it here. This is going to be translation of this kind of position here, right? And I'm going to multiply that scale in as well, okay? So we multiply this with scale and then we provide it with transform. So now what should happen is we should be submitting 5 different squares for rendering. They're all going to be blue, and they're going to be kind of horizontally spaced, like going kind of from the origin really to the right. And if they don't all fit into the screen, which they probably should, but if they don't, and they should be a lot smaller as well because we scaled them down. If they don't, we can always move the camera into a position that will be better. Okay, there we go. So we've got 5. You can see they're all spaced apart, and we can move just like that. Okay. If we were to make it even more exciting, what we could do is actually move all of this over and make a nested for loop where we go through X and Y, and let's just say we render a grid of like 20 of these. So all we have to do is move this way, change this to 20, X. So X is gonna be written like that, Y is gonna be written here in the Y position. And that's like it, right? So that's all we need to do. If we hit F5 again, we're gonna render a grid of 20 by 20, which is quite big. Hopefully the performance will be okay, because that is like 400 of these. And yeah, I mean, the performance is fine. So there we go, right? You can see that we've actually got a tile grid, and more specifically, we're kind of testing the actual, we're actually testing us being able to render objects with the different transforms. So what we're doing is we're submitting 20 different squares here, and I can put a triangle here if I want and render that on top of everything, like we were doing before. So if I hit F5, and it compiles our code, then we have our little triangle. We can move the camera, and we used to be able to move the actual squares, but obviously I took that away. Okay, so let's clean up this code a little bit. I'm just gonna get rid of the square, move speed and all of that, because that was something that we used just for fun. And I'll probably end up leaving this kind of grid here. So obviously this scale is something that you don't need to recalculate all the time, so you could just make it as static if you wanted to. And then, or just, have it as a member. And then really the only thing that we need to recalculate is the position. But because the position changes, you do need to recalculate this transformation matrix every time. But that's normal. Okay, that's pretty much it. Hope that makes sense. Now, it would be really cool if we could actually set a different color for each of these tiles, right? And then we can actually start basically having a bit of a tile map, even though this isn't really 2D rendering, as I'm saying. This is still kind of 3D rendering. It's not just 3D rendering because it's OpenGL, and OpenGL renders everything in 3D. That's not what I mean. What I mean is that the technique we're using to actually render this is kind of on a per object basis. So clearly that's kind of like a 3D way of doing things. Now, what we can do next time, and what I probably will do next time, is talk about uniforms and materials. So we can set up a very, very, very basic material system really easily, right? And I might actually even have next video be like a theory video about how material systems work. And then we can implement a very basic one, which is all we'll need for now, just to kind of get a little bit more flexibility. And then if I do that, like basically you can say that we're moving Hazel into an area where it could be used to make games, or it could actually be somewhat usable to do things like that. Now, obviously we don't have like textures or anything like that. That's something I really want to do as well, textures. Yeah, like it's kind of, I don't know, I feel like it's cool to kind of actually have something to show, and have something that's actually usable pretty quick, because you can see that we've got like a bit of an engine going on here, right? We're able to do all of this stuff without touching OpenGL or anything like that. It all kind of just works. We can submit stuff for rendering, and that's all pretty exciting. So let me know what you think about that. It's probably, I do want to add in at least some kind of way to set uniforms properly. And also we'll probably end up dealing with textures soon. And then after that, I think we might move into 3D and do meshes, unless people specifically really want me to do like a good, fast, blazing fast 2D renderer first, because if you do, then I might do that. Anyway, I hope you guys enjoyed this video. If you did, you can hit the like button. This was kind of more of a fun video where we actually played around with some stuff, as well as added in transforms. You can see how easy it is to just add in the model matrix and transforms so that we can actually render objects in different positions. You can help support the series by going to patreon.com/thecherno. Huge thank you, as always, to all the patrons. Remember, you can support the series there and get the next video right now. Next time, as I said, we've got so many things we can explore. Like, this is becoming difficult for me to plan. I really want to do 2D textures. I really want to do a very basic material system just so that we can set uniforms and textures and stuff like that properly. And then it's going to fork off into either a blazing fast 2D renderer and like doing a 2D renderer properly, basically, or kind of just continuing on with 3D, in which case we'll probably make like, where do we even start? We'll probably start with meshes, right? So we want meshes, we want to be able to load 3D models and process them, and actually apply materials to them and render them, and we probably want like a 3D camera, and that's just a huge kind of thing of its own as well. Let me know your thoughts in the comment section below, because this series is up to you guys. I'm making it for you, and I want to do whatever you guys want. I'll see you next time. Goodbye.